Good morning and welcome back to the third day. I have the pleasure of introducing my friend Andras Stipsicz from the Renyi Institute, who's going to talk to us about the genus function today.
Well, first of all, thank you very much for the invitation. I'm sorry I missed the first 2 days. So it could happen that I will repeat something which you already covered, and sorry for that. You can just stop me there. So the aim of the course is somehow to get a better understanding of what surfaces represent various homology classes in four-dimensional manifolds. So as always, X will be a four-dimensional smooth and for the most part always oriented and closed format. Manifold. Sometimes its closeness will be dropped, and we will consider also manifold boundary. And so here is the genus function. So what's the definition? So the genus function, dx, which maps from the second homology to the non-negative integers, and alpha is sent to the minimum of G sigma, where sigma is embedded, C infinity embedded surface in X, with the property that the fundamental class goes to alpha. Said differently, you just have X, you fix a homology class, second homology class, you try to consider surfaces inside, which in singular homology just represent that particular homology class, and you just take the smallest possible genus. So sigma is a closed oriented surface. So it's easy to see that if you represent a homology class with one surface, you can always increase its genus. You just add fake handles which do not influence the homology class, but increase the genus. Whether you can decrease the genus, that's a different story. You would like to see sort of fake handles you can erase, and then it turns out that they don't always exist. So there are some lower bounds on the minimum genus, and this is what we would like to understand. So here is a guiding principle. So Gx sometimes can distinguish homeomorphic but not diffeomorphic pairs of four manifolds. So we hope that somehow this function will encode or explain something about the exoticness of the smooth four manifold at hand. There is no hope or there is no reason to expect that this is a complete invariant. So it will tell us everything. You know, in four-dimensional topology, the main problem or blessing, depending on where you come from, for four-dimensional topologists, it's a blessing that the Whitney trick doesn't work. And you have to remember what the Whitney trick is. In higher dimensions, somehow, if you have two complementary dimensional surfaces, under some mild conditions, you can achieve that they intersect exactly as many points as demanded by their homology classes. And this is what you cannot do in dimension 4. So the failure of that says that besides the genus function, maybe these pairwise intersection numbers, the geometric intersection numbers, should play an important role. We don't understand how. So if you are looking for some great problems to contemplate on, this is one of the main issues in four-dimensional topology. Okay, so what do we do? What do we know about this genus function? So first, I will assume that we have some extra structures on X and alpha. So suppose for a moment that X is a complex surface, complex four manifold, i.e. complex two-dimensional, real four. So these are what I will refer to complex surfaces as opposed to complex curves, which are real two-dimensional surfaces. I know it's a little confusing, but that's what it is. C is a complex curve. So complex surface means that, you have to remember that the smooth structure is just the transition functions between charts are C infinity functions. Now we assume in this case that the charts are C2s themselves and the transition functions are holomorphic maps. In this case, we have the following adjunction equality. And in order to state it, I should check my notes because I always make a mistake with the signs. So twice the genus of C minus 2 should be equal to the self-intersection of the homology class minus C1 of the four manifold evaluated on the class. So how does this follow? Of course, this is just the instance of the Whitney formula. So note that the complex tangent bundle of X. So this is now a C2 bundle because X is a complex manifold. When restricted to C, will split as the tangent bundle of C plus the normal bundle of C. Right? Does that make sense? I see puzzle. Yes?
So what did it say? It's the evaluation of what?
There is this one?
Yeah, what is that?
Okay, so this is the first Chern class. Class of X, which now makes sense because X is a complex manifold, so the tangent planes come with an action of I. So these are naturally C2 bundles. This is a C2 bundle now. So it has a first and a second Chern class. The second Chern class doesn't contain so much information. It's the same as the Euler class, but the first does. And you evaluate the second cohomology element on this homology. So notice that this side of the equation is purely homological. This is homology / cohomology. While on this side, you see the genus. So this is somehow, let's call it like more geometric. So from the homology class, we can compute what is this genus, what the genus is. This is what we would like to minimize. Okay, so this is a simple splitting of the tangent bundle of X restricted to the curve. And so by the Whitney formula, we take C1 of Tx restricted to C is the same as the first Chern class of the tangent bundle of C plus the first Chern class of the normal bundle of C. These are all complex line bundles, and the first Chern class is nothing else than the Euler class of that line bundle, and this happens to be the Euler characteristic of C. This is this term. This happens to be the self-intersection. To see that, you have to remember how to compute the Euler class of a line bundle over a curve. You just take a generic section and you count the zero set. You count how many zeros it has. Well, a generic section of the normal bundle is just a nearby curve. So it will intersect exactly in that many points, counted with sign. And this is the side where you just take C1 of the tangent bundle and you evaluate it on the homology class. And I hope I got the sign right, because this is just 2 minus 2gc, and then you put it on the other side and subtract. Okay, so this is sort of the guiding formula where you see that somehow homological data can determine the complexity of the complex curve, well, under the assumption that we are in a complex surface and we have a holomorphic submanifold. And we would like to relax that, of course, because in our problem, everything is C infinity. Okay, so what do we do? So here's a remark. We can relax these conditions slightly. So it is sufficient to have X symplectic, i.e., there is a two form with d omega 0 and omega wedge omega positive, and C symplectic submanifold. I.e., omega restricted to the tangent bundle of C is symplectic on C. Then we have the same equality holds. This needs a little bit of a thinking. The first thing we have to clarify in our mind is that, okay, X is a symplectic manifold, but I would like to talk about the first Chern class of it. That makes sense. And it turns out that it does. In order to have a first Chern class, what you have to have on the bundle is a complex structure. So is it possible for a symplectic manifold to turn its tangent bundle, which is an R4 bundle, into a C2 one? And indeed, it's possible. So the ingredient, first, X omega symplectic, then Tx admits what is called an almost complex structure. So an almost complex structure is just a prescription, a multiplication of the complex unit I on the tangent bundle. So this is just a J, usually it's denoted by capital J, a bundle automorphism with the property that if you do it twice, you get minus the identity. Right, so it just turns the tangent bundle into a C2 bundle, and then the Chern classes are completely insensitive where the complex structure on the tangent planes come from, whether they come from a genuine complex structure or just an almost complex one. It's fair game. This class will actually make sense. It turns out, in fact, this is not needed here, that if you also assume that this J is compatible with omega in some sense, which I will not explain, then the choices of J is you can choose these J's from a contractible set. So in fact, this C1 is well defined. It is sort of associated uniquely to the symplectic structure. And the second thing we need is that J, maybe I will continue here. The second is that J can be chosen so that C X is J holomorphic, i.e., EC is J invariant. This is true if you have a symplectic submanifold. So this is where we use this assumption that for a symplectic manifold, we can pick this J in a way that tangents of C are mapped by this J map to other vectors which are also tangent to J. Stop me if I'm saying something complete nonsense or you got lost. Okay, so far so good. Well, if you have this situation, then my previous argument, which unfortunately I already erased, works exactly in the same way because this is only complex bundle theory and we just turn the situation into that. So this equality works not only when X is complex and C is a complex submanifold, but if X is only symplectic and C is a symplectic submanifold. This last bit is not absolutely trivial. This is sort of easy. This is a local computation on the tangent planes, the individual tangent planes. This is a little more involved, and I will not go into the proof of that. Okay, but this is still, we need these extra structures. So what do we know about this function? So G, sorry. So there are a few simple observations. So the first is that the minimal genus of a homology class alpha is the same as the minimal genus of minus alpha. So Gx of alpha should be the same as this because we can just flip the orientation on the surface and we keep the same map. Everything is the same except in the last minute I sort of flip the orientation of sigma. Similarly, the genus function of X is the same as the genus function of X bar. This is the same manifold X, except with reverse orientation. So we can always pick when we would like to understand the genus function of a manifold or the manifold with the opposite orientation. Again, the embedding is not changed at all. And there is one final little observation that if F is a diffeomorphism of X, then when we act with this diffeomorphism, with the induced homomorphism F star on the second homology, this doesn't change the genus. And of course, this is sort of a simple principle. Here's my X, there is a function F, and we have a representing surface which now represents alpha. And then we just take its image. So this is, I don't know, F sigma, and this will represent F lower star alpha. And then we can go back and forth because it's a diffeomorphism, so we also have an inverse. So this is again a simple principle, and sometimes it's very useful. So what do we know? What are the cases where we know the genus function? Well, there is the first and foremost and simplest example when X is just S4. That's quite lucky. The second homology is very modest, right? There is one element. It has one element, the zero element, which can be represented by a sphere, and then that's it. It also has the limitation of this approach to understanding exotica. For example, well, depending on your belief, whether the smooth Poincare conjecture is true or false in dimension 4, it just tells us that the genus function will never tell us anything about it, right? Because for exotic S4s, the second homology is still zero because they are homeomorphic. The function is very simple, so that's it. Well, the next and probably the most famous example is CP2. And here, so I will just tell you the formula. So fact, or actually this is a theorem of Kronheimer and Rovka from 94. And so the statement is the following. So in H2, CP2Z, which is just isomorphic to the infinite cyclic group generated by H for D not equal to 0, we have the following formula. GCP2 on DH, so D times the generator has minimal genus 1/2, the absolute value -1 times the absolute value -2. So this formula was conjectured by Tom, although I think he just denied that he ever conjectured that, but nevertheless, this formula was called the Tom conjecture, and then in 94, like 3 weeks after the Cyber-Witten invariants have been introduced to the theory, Kronheimer and Rovka came out with a proof of that. I'm planning to go through bits of that proof tomorrow morning, so I will just give you the main ideas, not the details, but so this is the Tom conjecture. There's always this problem. If a conjecture is a conjecture for a long time, even if you prove it, it will be called still the conjecture of the other guy. And you cannot attach your name to that, but you can survive. Anyway, so of course, we exclude D equals 0 because again, when D is equal to 0, we get the trivial element in homology, and that can be represented by a sphere. Notice then the formula does not hold. I mean, if you substitute D equals 0, then it gives you 1 as opposed to 0. So the formula is only for the non-zero multiples. Okay, so we will return to that question tomorrow, and we'll see how does it work. Another example. X, let's take S2 cross S2. So this is a simply connected four manifold, the product of two spheres. Now H2 is two-dimensional, isomorphic to Z plus Z, and it's generated by two classes, which I will write as S2 cross a point, the class of this sphere, and point cross S2. Okay, so I don't know, this is, maybe I call it X, and this is Y. And if I have to draw, unfortunately, I always draw this manifold as a box. You have to develop your own way to picture manifolds. Generic X is a potato, and S is a box. I'm sorry. And so this is an S2 coordinate, another one is an X2 coordinate, and then the two homology classes are S2 cross a point and point cross S2. They intersect in one point. Their self-intersection is 0 because you can play a little bit with this point. You just pick another point that moves away from the first, and then you see this homology between the two by connecting the 2 points with a little r. Okay, so what are the genera? And here's the formula. So, so suppose if alpha is A times X plus B times Y, and A, B are both non-negative, then the genus function of S2 cross S2 on alpha is, and again, we have to deal separately when one of them is 0. We have to be a little careful. So the answer is A minus 1 times B minus 1 if AB is not equal to 0, and 0 if AB is equal to 0. So let's spend a little time. I should have done it here. I will do it in a moment. But what do we, so where does this number come from? So well, we can come up with a representative of this homology class by drawing several copies of my favorite generators. So if it is A times X plus B times Y, we take A copies of these guys and B copies of those. And then we just compute the Euler characteristic. How do we compute the Euler characteristic? Well, we know the Euler characteristic of the individual component. And then this is not a smooth surface. It has transverse intersections, exactly A times B many transverse intersections. So whenever you see a transverse intersection in a little neighborhood, what you see are two disks in D4 intersecting each other in one point. This is the first instance of like when you have to close your eyes and then think in the fourth dimension. I like to quote my favorite movie, Back to the Future, where, you know, every time the guy explains like what happens in the future, in the past, he tells to the kid, Marty, you should think in the fourth dimension. This is where you have to start. So this is a little S3, and the curves intersect this S3 in a Hopf-link, and the Hopf-link is the boundary. The two circles are both boundaries of a disk. In D4, they intersect in one point. We take them out and we replace it with an annulus with the same boundary. So you take out these crosses and you replace it with an annulus, and you check that this is exactly what the genus will be. If you are less eager to use the Euler characteristic computation and you would like to see a visual, then what happens is that first you take all the verticals and then one horizontal. You turn this all together will be still a sphere, right? Because these are spheres and you just hook them up on one single sphere. And then whenever you give the additional new horizontal guys, then you can just compute how many such cells, how many genera you add to the picture. Again, Euler characteristic is the right way to do that, and this is sort of a pictorial motivation. Okay, so here is a little trick. So, okay.
How do you prove that is the minimum?
Well, we are not there yet, but I will just make a statement, and I will come back to that a little later. I should follow the time, right? Okay, we'll do that. Of course, how do I do it? I will quote a theorem, but we will get to that theorem at some point. But let me just contemplate a little bit about this assumption. So both numbers should be non-negative. If A times B is 0, meaning that one of them is 0, this means that we have sort of individual vertical or horizontal spheres only, and then you can tube them together, just connect them. I mean, you have to remember that this interval is symbolizing a sphere, and then you have these disjoint spheres. You just connect them by a path, you tube them together, and you get a sphere representing that particular homology class. But we still have when both are non-negative. What happens if both are negative? We know what to do because we just quote this little observation that it doesn't matter. We just take the same homology class with the opposite orientation. So the formula works really well when you just put absolute values there. There is a problem when one of them is positive and one of them is negative. But then you quote the other guy, this one, and there is this fantastic property of S2 cross S2 that if you reverse the orientation, it is still S2 cross S2. So the same principle works. And so at the end of the day, you can just put the absolute values to A and B, and you get the same formulae. Before getting to the question of how do we know that these are minimal, because we are just producing examples. I didn't do my assignment here. How do you get an example of a surface representing D times H in CP2 with that genus? Well, we go through the similar yoga. We just take CP2, and now we take D lines in generic position. So D complex projective lines. I did 4, and then you can continue. And you do the same Euler characteristic computation, and if you do it right, you get exactly that formula where D is non-negative, or actually positive, and then again, we invoke that principle to cover all the potential Ds. So this sort of question.
Sorry, can you explain what you do about the self-intersection points? Like what?
Here?
Yeah, I remember you said something about
So-
like locally, and then how do you change it so you can?
Okay, so I will do a real picture. So in the real version, when we reduce the dimension, we divide by 2, we see a cross. And so this is something like xy equals, sorry. So these are not the same axes. Okay, capital X, capital Y is 0. And you replace this by this little picture where X and Y, the product is some little epsilon. Now it will not exactly match, right? The other pieces of the curve will be a little bit off. So you have to do a C infinity sort of connection there. Does that make sense? So you can sort of write down it very explicitly. Most of the time is very clear. And then there is this matching thing where you have to pick a C infinity function which has, this shape. It's not real analytic, but that's okay. Does that make sense?
Yeah.
Okay. All right. So it's a good start, right? So S4, CP2, S2 cross S2. Let me give you one more example. There I will sort of only indicate what to do. So CP2 connected some CP2 bar. This should be very similar to that. These two manifolds are the two S2 bundles over S2. So there are two S2 bundles over S2. And you should remember that the reason we have two of those is because pi1 of SO3 is Z2. So I will make some statements, and if you have any questions related, maybe we can just sort of postpone it to the discussion session. Is that a reasonable compromise? Okay, so these are the two this is the trivial S2 bundle over S2, and this is the non-trivial S2 bundle over S2. And so here is what you do when you would like to understand the genus function here. So the second homology is again isomorphic to Z plus Z, which is generated by H, like the complex projective line in CP2, exactly the one I picked here, together with E, which is a similar projective line in CP2 bar. This is E because traditionally connected sum with CP2 bar is called the blow up of the manifold. We'll talk about it a little more. And this is sort of the exceptional divisor of the blow up. I will return to that soon. Okay. And so here is a construction. So take alpha to be A times H plus B times E, and assume that A is bigger than or equal to B. Then we can construct a complex surface, a complex curve in the following way. We take CP2 and we pick a point, let's call it Q, and take B lines passing through. So B projective lines through the Q, and then A minus B in generic position, not passing through Q. A minus B such. And then apply this blow-up procedure exactly at the point Q, So blow up Q to get CP2 connected some CP2 bar. Again, you get a curve, a complex curve with singular points. You have to count how many such intersection points you have and do the same yoga as before and get a formula which I didn't write down. But maybe again we can do that in the discussion session. So gives a formula for the genus. Once again, it requires this inequality. And what happens if it fails? Well, again, if both are negative, then you appeal to that principle. And if B is bigger than A, then you sort of reverse the orientation on the manifold, and then you are appealing to the next principle. And it turns out that CP2 connected some CP2 bar. When you reverse the orientation, you will get the same manifold. So again, you can use that. So it looks like it's a good start. The sad news is that it's also the end of the road. So these are the manifolds, at least in the simply connected case, for which we do know the genus function in its entirety. And I will tell you other examples where we know something, but now I will return to one of your questions. How do we know that this is really minimal? Well, we need a certificate, right? We need a way to certify that what we constructed, these surfaces, really minimize genus in the given homology class. And this is where the story gets complicated. So how to check minimality? And so my plan again is to list a few theorems, and then I'm planning to devote tomorrow's 2 lectures to justify partially some of those. So I hope it's mild enough the way I phrased. So we will not check everything, not even all the statements, and even for one statement, we will not get complete proof. But here are the ideas. So Seiberg-Witten invariants. So those will be your friends. This will be a function, and that function will help us to justify minimality in some cases. And this is how it looks. So the definition, Seiberg-Witten of X will be a function of the second cohomology of the manifold into Z, which counts solutions of a certain set of PDEs associated to a cohomology class here. So we start with a cohomology class, we'll set up a PDE, and we count how many solutions we have for that PDE, and that will be that number. It's much easier to say than to actually do it. And so we will spend some time tomorrow. I will try to explain some of, maybe not the constructions, but the problematic points.
To take the input to the second homology class, second cohomology class, do we have to fix a reference species structure?
So I will go to that. We will focus on simply connected manifolds where somehow the cohomology class will determine a species structure or will determine nothing, depending on whether it's characteristic or not. Okay, let's save the details for tomorrow. And so, here is a theorem the adjunction inequality, saying the following. So suppose if sigma is a surface in X, so that the self-intersection is non-negative, the genus is positive, and the Seiberg-Witten value on K is non-zero, such classes are called Seiberg-Witten basic classes. It turns out that although this function is defined on the entire second cohomology, its support is finite. So there are only finitely many such classes, and those are the ones which carry the most of the information we would like to have, at least in relation to the genus function, because if we have such a situation, then, and the formula goes as follows, 2g minus 2g sigma minus 2 is at least self-intersection plus the evaluation of K, maybe I will write this I did before, K sigma in absolute value. So you should see the similarity and also the difference with the adjunction equality. What are the similarities? Well, the terms appearing are very similar. We have the negative of the Euler characteristic of the surface, we have the self-intersection, and we have an evaluation of a second cohomology class on its homology. The difference is that this is not C1. There is no C1. It might not have any almost complex structure. X might not have any of those. And even if it does, there is no canonical choice of those. So those are substituted by the Seiberg-Witten basic classes, by those which admit solutions of this PDE. And the other more important difference is that we are not having an equality anymore. We have an inequality. So you should see that somehow if we assume X to be complex and sigma also complex, it's a very rigid situation. The genus is determined by the homological data. You cannot expect that in this C infinity setting. As I told you earlier, if we have a smooth manifold and we have a sigma, we can always increase the genus by adding fake little handles. So you cannot expect any inequality. You don't know whether your sigma is created by adding these fake guys, which doesn't change the other side of the inequality. So this is the best you can expect. And miraculously, the best what you can expect is actually true. Okay. So this is one statement. And then here's another one. Theorem is the theorem of Taubes, again from the early days of Seiberg-Witten theory, saying that if X is symplectic and there is a mild assumption that the B2 plus should be positive, then Seiberg-Witten of X on C1 of X is plus or minus 1. So this just says that if we have a symplectic manifold and we pick an almost complex structure, that allows us to talk about the first Chern class of the tangent bundle. And this is always among the classes where the inequality is in effect. It stays a little more. We need not to be equal to 0. Actually, the value is plus or minus 1. The sign depends on a further choice, which I don't want to go into. Okay, so if you put these together, we get the extension of the adjunction equality for symplectic manifolds and symplectic submanifolds to symplectic manifolds and any C infinity surface, while satisfying this assumption. So the final blow is a theorem of Ongewaard and Sabot, which says the following. Where did I write that? So X omega symplectic, C symplectic submanifold, surface, sigma C infinity embedded surface. If their homology classes coincide, then the genus of sigma is at least the genus of C. So what does this mean? Well, this is exactly the certificate we were looking for, or said more precisely, at certificate we were looking for, that if you have a homology class and it can be represented by, and you are in a symplectic manifold, and your particular homology class can be represented by a symplectic surface, then that has minimal genus. You can almost get this theorem by putting together the adjunction inequality and Taub's theorem. There is an annoying little detail, this one. So, they had to get rid of that assumption, but it made the paper to be accepted in the annals. So you could imagine that it's not a minor detail. It's a real complication, and we will not touch that at all. What I'm planning to do tomorrow is to give a little idea why this holds, and we will do that in the Cyber-Witten setting. And I will talk a little bit about this theorem, but in a slightly different setting in the Hegard-Fleur world. The two turn out to be equivalent. I will not go into the equivalence, but I would like to sort of show you principles and ideas in both theories. And this is the really useful formulation. If you apply this to all my previous examples, all the manifolds were complex, in particular Kähler, so they were symplectic manifolds, and all the submanifolds we created were complex submanifolds, so this principle applies to them, and this gives us the justification that they are of minimal genus. And so how do we do with time? Okay. So there are two other things I wanted to explain, and I won't do that. But the first problematic point, the first manifold for which we don't really know the genus function is the first problem is CP2 connected twice CP2 bar, where we will lose that fantastic symmetry. You remember that here we flip the orientation, we still get a symplectic manifold, we still can use the Oswald-Szabó theorem. If we do that here, it's not symplectic anymore. And we don't know what to do. And I will tell you a little bit about what we know about the genus function of this manifold, but we don't know the entire function. And the other thing is that, okay, so what are our goals? Well, what is the goal of a decent four-manifold topologist who wants to study exotic manifolds? The goal is to see whether there is an exotic S4. And I told you this genus function is completely insensitive for that. So that's very sad, unless we extend this whole notion. So the extended genus function so take X as before and consider X circle to be X minus the interior of a four disk. So you just take a point, you take the little neighborhood of that point, and you just sort of erase it from your manifold. You get a four manifold. So this looks the usual potato. This is my D4. And then we get a manifold with boundary. The boundary is S3. And now you consider Gx to be a function now, not only on the second homology, but you take the second homology of X cross all knots in S3. And then we just ask the same question. So an alpha and a K is mapped into the minimal genus of F, where, as before, F, boundary F, is C infinity embedded into X naught, boundary X naught, so that the fundamental class, the relative class, is just alpha, and the boundary is K. Said, more pictorially, you just draw. Now I use colored chalk. We are almost up in time, but here is a knot. It's inside S3, and we are looking for all the surfaces it bounds, and this goes into X naught and represents a fixed homology class. Notice that I wrote H2 of X, although I should have written this relative, but they are isomorphic because the boundary is just S3. Okay, so we will sort of try to get some knowledge about that function. This generalizes a very standard question of like which knots are sliced in D4, where this portion is completely out of the picture, and you would like to see which knots map to 0 under this map. And we hope that maybe this will not classify all 4 manifolds, but it's a one step closer. And maybe what you really have to put in the pot is one more ingredient. How do intersections, what's the difference between algebraic and geometric intersection points? But this is the point I should stop today. And as I sort of explained, I would like to spend tomorrow talking a little bit about this inequality, and then in the afternoon about a theorem which resonates with Hobbes' theorem. And then we will return to these minimal genus problems after we have all these tools. Questions? Yes.
The definition of the new genus function, should that be relative?
Here?
Yeah.
Yeah, so that was my remark that strictly speaking, it should. On the other hand, this is canonically isomorphic to that because the boundary happens to be S3. But very good. You have to be pedantic, right? After all, it's mathematics, so it has to be precise. Although this is why God gave you hands to wave them. Any other questions? Yes?
For CP2 connected some CP2 bar, what happens if A is greater than 0, greater than B?
Say it again.
What happens if A is positive and B is negative?
So this is where you flip the orientation.
But you flip A and B together. I mean, one is positive, one is negative. Just
you are right. Then I forgot to tell you one trick. That you can always assume this. You can always assume B to be positive because there is also a reflection in homology. This is where the third principle comes in, that you have a self-diffeomorphism. There is a self-diffeomorphism of CP2 bar to itself, which maps alpha to minus alpha. So you can flip the sign of this guy by a self-diffeomorphism. So does that make sense?
yeah, that makes sense.
Okay. Sorry. Yeah. I listed 3 things and I only used 2. Should make you suspicious. Yes?
Is there a quick example in which the genus function can be used to detect an exotic pair?
Yes. So for example, this is one of those. So if you go through the yoga, actually very similar to what we did here, you will get the answer that if alpha squared is 0, then this is 0. Okay, so in this class, in this 4 manifold, every homology class which has 0 squared can be represented by a sphere. And then there is an exotic construction. I will talk about these constructions on Monday. And there you will find classes which have 0 squared, but this is definitely positive. How do you show that these are positive? Well, you use these formulae, or you appeal to to the Oswald-Sabo symplectic fold conjecture. So you don't have to go very far to find such examples. The construction of those examples is a little bit tiring. I will not do that today, but maybe on Monday I will refer back to this remark of mine. Not for S4, unfortunately, but we hope that I was planning to talk about potential counterexamples, and maybe I will do that on Sunday. Okay? I know it's always convincing when you can do something with these, but we can do very little so far. Yes.
Is there ever like a situation where you would want to consider like the thing is diffeomorphic to it? So like I think it would be like CP2 bar connects some S2 cross S2 instead of CP2 blown up twice. Like, you know, does I was thinking about it differently, change what types of tools you have available?
Yeah, so this is the same, right?
Yeah.
Yes. So before coming here, I thought that we have a theorem which uses this decomposition as opposed to that.
Mhm.
The theorem fall apart. I can still tell you the details, but it doesn't bring you far. But there is this idea. I don't know a single situation now where it is more beneficial to have this picture than that, but I have faith that it will happen. Yes.
Is the implication that if alpha square is zero, then the genus, so for CP2 blown up twice, you wrote that if alpha, yeah, that. Is it just an example or is that an easy?
It's very attached to that particular manifold. It still holds when CP2 you blow up 3 times, and then I don't think it holds ever after. For if you take 9-fold blow up, it clearly doesn't happen because those manifolds admit elliptic vibrations, so they have symplectic manifolds which are tori in classes with self-intersection 0. So it should stop. Probably it will stop after that. It's a particularly curious situation, and in fact, we took those exotic copies of that manifold and we tried to find spheres in them. And it's not only that we didn't find self-intersection 0 spheres, we didn't find any spheres, which doesn't mean that they don't exist, because we have no idea how to handle the negative self-intersection guys, but it might happen that some exotic manifolds just don't contain homologically essential spheres. It could happen. So the short answer is that it's not a generic phenomenon. Okay. Can we call it a day for me?